An engineer, so he's this kind of type of people that we like a lot. He's this kind of type of people that always help us a lot in many of the ideas that we want to realize. Actually, he's here with us those days because he's participating in the workshop that we are conducting together with Anupama and together with the students of the 2 years master, and he will be helping us to build the installation, the one-to-one scale pavilion that we will be building in June in a public square in Raval. So just allow me to read a bit about Arndt for the ones that they don't know. He's from Stuttgart, Germany. He graduated in civil and structural engineering at the University of Stuttgart, and in 2004 awarded his PhD thesis, which is a very interesting topic, structural behavior and bracing of high-rise tubes for solar updraft towers. You need to explain this a bit. It seems like really interesting for what we're doing here. So Arndt, from 1996 to 2003, he was a research assistant at the Institute for Structural Design, and in 2003 he then commenced as structural engineer with Schlaich, Bergermann and partners in Berlin and Stuttgart until 2011. During this time he contributed to projects in China, Germany, India, Spain and USA. Since July 2011, he has been a researcher at the Chair of Conceptual and Structural Design, TU Berlin, studying the dynamics of bridges, pedestrian-induced vibration, experimental model analysis, lightweight structures, lightweight concrete, structural control, and more. So he is as well in between academics and professional world, which means that he's going to love our place and he's going to help us a lot. Thank you very much, Arndt, for being here today.
Hello, everyone. Hello, everybody. Thank you for this nice introduction. And actually, to my PhD thesis, it was about updraft towers, and it's the idea how to use the chimney effect to produce solar energy. And Jörg Schlaich tried to establish these ideas now for several decades. And actually, in Manzanares here in Spain, there was in the mid-80s a prototype of this tower. It was a tower about 150 meters height and at least 5 kilowatt of electrical power. And unfortunately, it's only worked for 7 years. After that, it had to be demolished. But the basic idea is, can we use concrete tubes of 1,000 meters high to produce electrical energies from the greenhouse effect? And the idea was the structural investigation of these tube structures, but complete different story. I want to talk today about dynamic lightweight structures, and this is something I have worked now for several years on with Schlaich, Bergermann and partner on the one side, and at the TU Berlin we have several research topics actually dealing with lightweight structures. And now in my presentation you will see why it's dynamic lightweight structures. The title shows us a problem which I will show to you in detail. So the motivation is, so to my mind, lightweight structures are very interesting because they reduce the material, they are very sustainable and also very elegant structures. And from my early studies at the University of Stuttgart, I was involved in these lightweight structures because of the tradition in Stuttgart. We had Jörg Schlaich with the Estadio roof in Munich in the 70s, and all the education is also in Stuttgart around lightweight structures, if you are interested in lightweight structures. And to define from a structural point of view, what is a lightweight structure, I will give you or present you some examples here. The latest project here, or one of the latest projects here by Schlaich Bergermann, you will see some of these lightweight structures. This is something I understand, and if you take the lightweight, the term of lightweight structures in the light of footbridges, for instance. This is a very lightweight footbridge. It's a cable-stayed structure. You have a mast here and the cables here. and you have here a very slender deck, comparable slender deck, and you can see this was tension structure. You can use it also as a compression structure. You don't have a tension. Here up cable, you have a bow or an arch here working on compression. This is something I also subsumize under lightweight structures. Look at these pedestrian bridges. You have spans of more than 100 or 150 meters. And actually, if you would like to cross these rivers with a beam structure, you would have a tremendous height of the girder. So actually, this is something what I call lightweight structures. This looks even more lighter. This is a cable-supported bridge near Stuttgart, where I have worked as a structural engineer for the dynamics for this bridge. And actually, this is here a suspension cable, and you can see here the deck with a width of almost 4 meters. Here you see the bridge, and here is the river Neckar in Stuttgart, where the bridge has been built. And so the office of Schlaich Bergermann works a lot with footbridges and pedestrian bridges. On the other hand, they have very good experience with lightweight roofs, membrane roofs. You can see one of the earliest membrane roofs which has been built. This is the Gottlieb Daimler Stadium in Stuttgart. This is, let's say, the prototype of the membrane roofs. And what you can see here is a very light structure with membrane here. You have a cable ring here, and these are not girders, these are only cables here, and you have a big compression ring here. In terms of structural engineering, you can say it works like a spoke wheel, more or less, but actually the point is that this roof is comparable light and easy to construct compared to other large span or wide span roofs for stadias. And also lightweight structure, this is a structure in Stuttgart. This is a tower, panoramic tower in Stuttgart. And actually you can see that it is a kind of cable net structure here outside, where the stair is attached to this cable net structure. And to get the cable net structure work here, because it's all in tension, you have to have here this post inside for the compression. So this is also something I would have in mind when I talk about lightweight structures. And another project, unfortunately, this has been already demolished because it was built in the 70s, and this was a design by Jörg Schlaich. It's regarding a cooling tower. What you can see here is an old concrete cooling tower as it's built everywhere. You have wall thickness of about 20 centimeters or 30 centimeters here in this concrete, and to make it more lightweight and to reduce the amount of materials, Jörg Schlaich invented here this cable net cooling tower. It's the same principle you have seen with this panoramic tower, where you have here the post, where the compression force is introduced to span here the membrane or the cable net. In this case we have a cable net and only a metal cladding on it, so completely different idea compared to this cooling tower here. But actually these structures are really lightweight, and with this lightweight we have also problems with dynamics. Unfortunately, sorry, I'm a structural engineer, and so I try to give you a little bit insight into the physics to understand what happens there. And what you can see here is, let's start with this here, different types of excitation. You have a structure, and civil engineers or structural engineers talk always about loads and excitation. And actually, if we talk about the dynamics of lightweight structures, we have also to keep in mind that there are several excitations. These excitations result from traffic, humans, from machinery, wind, and at last but not least of earthquake, but at least lightweight structures are not prone to earthquake disasters. So actually you see here these yellows yellow written points, humans and wind are the most critical things to our kind of lightweight structures. And actually you see here, because you have bridges and stands in stadia which are excited by the humans. I will show you some examples later on. And also the wind is a real issue for bridges, the towers, cooling towers, cable net structures. And there are some phenomena like gustiness, vortex shedding. These are all words. I will show you some pictures just to get you in a little bit into this world of the dynamics at the end of my presentation. The problem in dynamics, if you have lightweight, they are always prone to vibration, but vibration is not bad. The problem is resonance, and I have put something here in a nutshell just to give you the basic idea. Maybe you know about the term of natural frequency and mode shape from your studies. And therefore, I just want to remember you about these terms. And structural engineers always have a toolbox, which is called a finite element program. This is the wonderful toolbox. You can put everything in and almost calculate a lot of things. And what you can see here is a picture of a cable-stayed bridge. You have seen already this bridge on a slide before. This is the bridge in Mettingen or in Stuttgart. And what you can see here is the cable structure. You see the mast, you see the ramps here and the deck. And then the structural engineer calculated the natural frequencies. There are several natural frequencies, and I picked out one of them. And what you can see here is a mode shape. This is the deformation under this vibration. And this is, for instance, the mode shape for a frequency of 0.5 Hertz. This is a natural frequency, a frequency of the system. And actually, you can compare it like a guitar string. If you have a guitar string and you attach this guitar string, this will vibrate in a certain way. This gives the tone. And actually, this guitar string has a natural frequency of, say, 1000 Hertz. And in our case, this bridge has a natural frequency of 0.5 Hertz. So actually, the problem is here that each structure has a natural frequency, and you can excite this natural frequency. Also, this floor has a natural frequency. I try to excite, but nothing happens. Frequency is too high. But what happens if we have a natural frequency close to the frequency of the excitation? That's something I want to show afterwards. There are several cases which are for the structural engineer of high importance. So actually I have found on YouTube a nice video where the concept of resonance is clearly shown. What you can see here is two persons here in front. You can see one here at the back, and they found the natural frequency of the structure. And now see what happens. So actually this is a horror for a structural engineer, because you are thinking about failure of the structure, ultimate limit state and everything. And actually the problem is, if you think about a deflection like this for static loads, you would never try to attach this load to the bridge. But in this case, in resonance, you have very large deformations which does not fit to any static load. And if you have resonance, you have sometimes an amplification of 80% or 150% of a static load, compared to the case when the people just are walking or here standing on this bridge. So actually this is a typical kind of resonance, and I would say it's not relevant for design, because this is something I would call vandalism. So actually this is not the typical design case for engineers. But let's talk about wind-induced first, before we go back to this pedestrian-induced vibration, because wind-induced vibration is also very important for these lightweight structures. And I want to show you an example here. This is a membrane roof here of the Warsaw National Stadium, and architects were Gerkan, Mark and Partner in Berlin. and structural engineers Schlaich, Bergermann and partners. And what you can see here is this membrane roof here, and you have also a foldable membrane structure inside here, and you can see here the cables here, and this is the parking lot for the membrane part here, so you can open this part here of membrane and pull here the membrane here in this kind of parking lot. And actually, because this is a landmark of Stadia, and the people in Warsaw wanted to have this as also to print postcards for the European championships, they introduced here this kind of mast here. And this kind of mast is for structural engineers a real challenge. I'll show you on the next pictures why. So just to get you a little bit more into detail here, this is the roof structure. The permanent roof is here, and you see the cables, and at the end of the cables you have this steel needle here where the parking garage for the membrane is located. And actually this steel structure here is typically prone to wind-induced vibrations, and we know this problem, for instance, from chimneys. Chimneys have also the same problem we can find for this steel needle at the Warsaw Stadium. And to explain the problem to you, I have here found from a lecture at the TU Berlin a picture where you see the airflow around a circular cross-section, and you see we have a very smooth flow here, and suddenly here there are some turbulences appear, and actually here some eddies delaminate here from the structure. And if you put this more abstract way, you can see the eddies here, and the problem itself is not the eddy, it's that they have a periodic delamination phase here at the cylinder. And what they do is they put forces in perpendicular to the wind directions to this cross section. And actually this is a problem, a real problem, if you get in resonance, because actually then suddenly this tower starts to vibrate perpendicular to the wind direction. In the chimneys, they attach these scruten here. The scrutons, it's an easy way to change the flow, but you have to be aware. And for the Stadia roof in Warsaw, the architects don't want to have these kind of scrutons here to avoid this. So we had to do several tests and calculations to make sure that nothing will happen. In this case here, this is a windmill. They have a real problem with the vortex shedding, and actually the result is like that. And actually, as we are now in Germany without atomic power, we want to have more windmills, and this is a kind of research area how to make these structures more lightweight but not prone to these wind excitations. Another failure here, this was a great disaster in Great Britain in Ferrybridge in 1965. 3 of these cooling towers collapsed by vortex shedding. You can see the wind came here, the eddies started from here and hit always on these towers. And the towers started to vibrate, and there was one worker taking one picture when this accident happened, and you can see the shell structure looks like an 8 and not like a circular, and this comes from vibrating of this shell structures. And another example, and this is quite critical also for the pedestrian bridges, is the problem of flutter. You know maybe this Tacoma Narrows Bridge, which was built in the US in the early 30s, the last century, and actually this was a kind of record. They had a very, very slender deck, and all in a sudden there came a certain wind speed, the deck started to vibrate here. And you can see these deflections here, and actually it swung or wobbled about 10 or 20 seconds, and then the bridge crashed down. And actually this was one of the first bridges where this problem of flutter occurred, and nowadays you have to check all of the bridges for this problem. So this was wind-induced vibration. If we are talking about lightweight structures, we have also human-induced vibration. And one classical example to explain you what is about synchronizations or how big the forces can be for this human-induced vibration. I always show you the picture here. Sorry, it's a very bad picture of stands and human-induced vibrations. And I have also found here this small video just to make you aware of the problem. And this guy is not here to calm the people down to avoid structural damages. He's responsible for the party in the stadium. And actually what you can see is, look, these guys are started to wonder what happens there. And here you can see, hopefully a little bit better. Now you see 3 or 4 centimeters movement of the structures due to the jumping of the people here. And this is a real disaster if you are a structural engineer and you get a call on Saturday evening from the owner of the Estadio and asking what to do now. And actually, you see this. And would you feel safe if you are part here? So actually, you see, this is a problem of the resonance, and actually you have a lot of mass here in this structure. This is a very, let's say, solid concrete structure, but this mass can excite it to such amplitudes by all the people. And that's a problem also when we are talking about pedestrian-induced vibration. This is something we have in common when we are designing pedestrian bridges. Also, if we design floor systems and buildings, because nobody wants to have these vibrating floors. Actually, understandable, because it's a real health issue in the long term. But let me start with a very nice bridge I found in Lyon. And this bridge was built in 1852. And it has a span of 75 meters. And it's a very nice bridge. It's a historic document. And actually, I tried to walk over this bridge, and this bridge is really lively, wobbling. And the interesting thing is that nobody cared about there for 150 years. And it was not a problem of fatigue or a problem of comfort. So actually, I want to show you with this picture, lively bridges are possible. And also, if you see the long term of use of this bridge, it's not a fatigue problem or something like that. You can do it, and the bridge is accepted by the people here. And this leads us to an investigation we did. We were involved in a EU-funded projects about pedestrian-induced vibrations of bridges, and we make a questionnaire and ask the people crossing 2 different bridges. And the funny thing is, these 2 bridges have the same natural frequency and the same accelerations if you walk across. And also the people are almost of the same age and of the same social group. So when we ask here, when they pass, what do you feel, what do you think about the vibration? And only 10% said, oh no, I feel disturbed by the vibration. And this bridge here, the same accelerations, about 40% of the pedestrians said, okay, we don't like this vibration. And the problem is now for you or for me as a designer where to go, because actually you cannot avoid vibration. And what is comfort, what is not comfort. And one of my explanations is that this bridge, I would say this bridge gives you a promise of stability. And the people are worried about this vibration here on this bridge. And here, okay, they say this is a lightweight bridge, it's slacky or wobbling, and so actually they don't worry about the problem here. And in this case, I will show you a video. You can see what happens here. This is a video. You see these four guys, they are walking in synchronous, so like in a stadia roof, in the stand, they are almost marching, and you can see here the amplitudes. Only 4 persons, no? But they have a trick. They have a metronome, and they know the natural frequency of the bridge. And now look at the lady here. She tries hard to walk, and now she gets some problems here to walk. And now the bridge starts again to vibrate. She wanted to leave very fast and quick. So this is a problem. It's structural engineering that you have to think in advance of this problem and think about comfort problems and everything like that. And the problem becomes greater if you have now not these low densities of 0.3 here, but you have, for instance, here pedestrian densities of 1.5 meters per square meter. And actually you can see here a picture from Mecca, all the people's walking here on these bridge decks, and there is a huge dynamic force and excitation of the bridge. And one famous example is this Millennium Bridge in London by Norman Foster, and the engineering was done by Arup, where you have a problem which came up in 2001 for the first time. So this is a video from the inauguration of this bridge. And now look at that. The people are going to walk like sailors. And look at the deformations here. You can see here. You see? And they are now walking in resonance here on the bridge deck. And actually, that's not a question of comfort. This is a question of serviceability or usability of the bridge. And after 3 or 4 weeks, the bridge was closed, and they put a lot of dampers inside to avoid this problem. But this problem occurred for the first time in the bridge design. So actually, it's a very important aspect, but you can see as crowds are getting denser, we are also struggling with this problem for footbridges. But you see, good vibration, bad vibration, what is the difference? It's a question of comfort. There's also an example where we used vibration to make people feel about vibration. This is an example from there's a pedestrian bridge in the Deutsche Museum in Munich. This is a technical museum where you can see trucks and machines and everything, and they have a special department also for bridges, and Jörg Schlaich designed here a small pedestrian bridge which is really lively. And this bridge is instrumented, and it's a real nice lab for the children to go in on the bridge and to play around with vibration. And actually there's another example by Anthony Gormley. He had in 2012 an installation in Hamburg where also Schlaich Bergermann was involved. And we have here a very huge platform which hang on 8 cables here from the roof structure, and the people were invited to walk up and to feel the vibration. And the funny thing is that all the people together excite also the platform. So this is a kind of interaction, and for me a very good example how to take the dynamics also to get an emotional aspect of an sculpture. So, very nice project. And if you don't want to have this large vibration, you have to think about damping. And damping is almost done by these tuned mass dampers. And you can see this is a very technical issue. You have some mass, you have a spring, and you have a dashpot. And actually, if you have done your design well, you find some place where to attach all these boxes. And this is an example from the Millennium Bridge, where they have to put all these huge dampers here inside. And sometimes you can hide this, and sometimes you have the problem that you cannot hide it. And then actually the discussion with architects is to show the dampers or not to show the dampers. But in any case, it's a problem. If you don't take these vibration issues serious from the early design, then you always get into problems. And actually the worst scenario is that at least you will get a call by the owner and he's not happy with this bridge because of the vibrations. And afterwards doing this repair work is really bad thing. So actually that's why we at Schlaich Bergermann used to take all the thoughts about dynamics and vibrations into the early design stages. That's a very important aspect. I want to show you two projects now, a little bit more in detail. This first one is Sassnitz footbridge. This is at the Baltic Sea in the north of Germany, northeast of Germany, and you can see this nice footbridge here. And this is a cable stayed structure where you have here cables and the mast. And actually, in this case, we have to try to think about this vortex shedding, also let's say the wind-induced vibration, and also pedestrian-induced vibration. And sorry, this is in German. This means aerodynamic optimization of the cross-section of the bridge. And I want to show you just two things here. So this is the cross-section you can see here. The cross-section, you have here the walkway, and this is a construction here for the cable structure here to be attached. And actually the pedestrians will walk here somewhere. And we have tested several situations with wind from both directions, so from left to right and right to left. And, oh, sorry, I just want to show you the video. So, once again. So this is the old section where we have done the design, or from the structural point of view, this is the section how it looks like, what we need, and steel plates and everything. And this is what the wind engineer recommended. He just added a small plate to the cross section, and the effect is tremendous. Sorry, I'm a little bit here. Sorry. Once again. So now, cross section again. The design from the structural engineer and the attached plates from the wind engineer. And now we put this model in the wind tunnel, and you can see here the rotor plates which generate the wind, and here is the old cross section, the new one with the plate, and now we are increasing the wind speed at different steps, step 4, and you see the old starts already to vibrate. And this is a full scaled model, so actually what you can see, this vibration is introduced by a wind which is a realistic wind at the sea. So actually just attaching or changing the cross section here has a tremendous influence on the stability of the cross section. And the next step is to check the dynamics of the pedestrians. And as you can see here, we have a hollow box here where we can hide all the dampers. We don't want to show them. And in this picture you can see here these small gray dots. These are small openings where we can attach this damper in the cross section. So this is an essential part of the design here. And afterwards we try to excite the bridge and do some measurements and do dynamic testing. And sometimes, or in 50% of the cases, it's not necessary to install these tuned mass dampers, because the bridge is more robust and has more damping, and it's harder to excite. And this is something you cannot calculate. So you need a lot of experience, and you need also a lot of knowledge about the behavior of the final bridge. And we decided just to make at the end a test and decide afterwards if we go for these tuned mass dampers or not. And the other thing, the other project I was personally involved is called Slinky Spring to Fame. And there's an artist, Tobias Rehberger, and he wonders if it's possible to build from this toy. You know, there's a toy with these spirals, and if it's possible to build bridges with these toys. And the first ideas looks like this sketch. So this is the idea of Tobias Rehberger, and now is the question how to make a structural concept for a pedestrian bridge. And we have a span of 70 meters. And the question is now, if you take a standard beam bridge, you won't see here nothing else instead of the girdle. You won't see these spirals here because of the structural height of the beams. So actually this is quite a challenging task for the structural engineers. And what we decided to do is that we have here some special ramps, 2 of them, to get the necessary height to cross the canal here. You can see here is the canal, and the second ramp starts from here up to here, and this is here a so-called stress-ribbon bridge. The stress-ribbon bridge has a very big advantage. You can see it here in the cross-section. It works like the cable structure. You don't need a structural height for bending. You have here a cable with a certain sag, and you put on the concrete panels on this cable-like structure, and we have here a deviator here on this, and this cable runs here from here to here, and here we have the backstay to anchor the tension force in the ground. And this is a very nice idea, because in this case you have only structural height of 20 centimeters for a span of almost 66 meters. And you can see in these pictures now a very, very slender structure, but it's lively and it's lightweight. So actually we had to deal also with the dynamics and wind tunnel testing and everything. And actually some pictures here. You see the spiral very nicely wrapped around the bridge, and no structural height or structural beam is disturbing the view on the spiral. And you see some impressive, nice photos here. And you can see here, this is the stress ribbon. We don't use cables for these bridges. We use a steel plate. This steel plate had a width of 60 centimeters and a height of, let's say, 30 or 80 millimeters. So it's a stress ribbon, not a cable. And this colors and illumination is very nice during nighttime. So, and actually, as I'm a researcher at the Technical University, I want to show you something about the dynamics and also what to do with the lightweight structures. What is real lightweight for bridges? This is real lightweight, sustainable, and very less structural effort or structural material. This works all in tension, no bending, and this is a very effective system for pedestrian bridges, but it does not meet our comfort requirements. So actually we want to have a concrete plate or something to walk on, but in terms of efficiency and lightweight, this concept of the stress ribbon is very interesting. And what you can see here is one of the first stress ribbon bridges built. It has here some large abutments, because you have to anchor the tension force in the stress ribbon, and the detail looks more like that. You have here the stress ribbon, a steel plate. Nowadays we take a steel quality of S690, very high quality, and we apply here some concrete panels. but also take care, we have also here this gap between the concrete panels so that there will be no bending in the system, and just the cable structure here. And at the Technical University, we ask ourselves, can we reduce the thickness of these plates or the thickness of the stress ribbon? And we use this stress ribbon made of carbon fiber reinforced plastics. Tremendous tensile strength can be used here, and the thickness of this ribbon is only 1 millimeter. It's very nice, but actually it will have a dynamic problem, as I will show you. But here you can see the stress ribbon bridge with concrete panels here attached on. And in our lab we have only now a span of 13 meters built, but for our investigation it's very nice to do some certain tests. And one of these tests is regarding pedestrian-induced vibrations. And look how this bridge started to vibrate. It's a real problem. And that's an issue. If you want to have lighter footbridges, you have to think about these pedestrian-induced vibrations here. And one of these points we try to find out or find a solution are semi-active or active vibration control. And for this we have now attached, beyond all the posts and the hand railing and the carpets, some muscles here. What is a muscle? This is a special unit, I will show it later on, where we can introduce here at the defined measure some forces. And we have additionally now a central processing unit where we collect data from the bridge and give commands to these muscles. And actually the idea is of this muscle that we have a valve here and some air pressure, and we can control the air pressure in this muscle here. And actually what happens if we inflate this muscle, it starts to contract and produces a tension force here. And actually what we do here is we introduce here in the post some forces to act against the vibration. And this is some stuff we need to attach also to measure the displacements and to know where the position of the muscles is. So all together we have this unit and the computer with all the algorithms. And what comes out is if you have a pedestrian walking on this small bridge, you see the bridge starts to vibrate. And now here the pedestrian leaves the bridge, then you have a free vibration, and it takes about 100 seconds that the bridge will not move anymore. So actually you see this is a problem of damping. So this is a very low damping. And if we have this system running, you see you will only get up to 2 meters per square second. It's enough. It's more than enough, 2 meters per square second, but you can see the effect of these muscles working against the vibration. Also, if you have here the free vibration, it's very short, only 5 seconds, and the bridge will not move anymore. So this is one of our research topics, and I just want to show you one video how this will work without pedestrian. You can see we put some air pressure here in the muscles and you can excite the bridge, and this is the way how you can act against the vibration of the bridge. So this is some PhD work done here at the Technical University by Achim Bleicher, and he developed also mathematical algorithms to control the structure. So, conclusion. Lightweight structures, I showed you they are elegant, and we try to minimize the use of material and therefore to build more sustainable structures in a true sense. But I have also showed that they have a problem because they tend to be lively and they can be excited very easily. But with special engineering efforts regarding dynamics, these problems can be solved. And one thing we should always think about is to avoid resonance. This is the critical point. And from the research, I'm sure that new materials and advanced technologies like the semi-active vibration control will enable to go beyond the present limits somehow. Thank you very much. So usually there's now questions or discussion. Are there any questions or comments and remarks?
The Danish stadium in Stuttgart, you showed the membrane, the lightweight membrane that made up the roof structure, but the structure itself was held up by cables. Is there much work being done? I'm not sure that, I assume that there might be, to replace the cables with the membrane itself, making that the tensile component?
No, actually the problem is that the tensile strength of the membrane is not sufficient. When I'm on the right track with your question, you ask if the membrane structures work without tension elements like cables or something like that. That's not possible because you see the tensile strength of these membranes is too low. And actually you see sometimes in these stadiums we have bundles of 8 or 12 cables of such a diameter. And this is a conceptual issue that these structure work like a spoke wheel. So actually in your wheel you have a spoke. This spoke actually, this structure work like a spokes wheel, and you have these spokes which are pre-tensioned. And the membrane, if you think of this spoked wheel, is just cladding beside. You need some pretension in the membrane that it will not start to flutter in the wind, but actually, or to give us a certain form. You can make a hyperboloid or something like that out of it, but it's not possible to use this for the entire roof, to my mind. Let's see.
The bridge with the form helicoidal works better for tension than the bridges with the cables.
You are talking about this bridge?
The last bridge that was the
Slinky?
yes, I think. Yes. It worked better to the tension force than the bridges that are with cables.
So actually there are several ways to design the bridge. Actually, you see there are some suspension. There are also some suspension bridges where you have these high masts on both sides and you have a cable and hang up the deck from this cable. But in this case, the artist, Tobias Rehberger, wanted to have just pure spirals and not an interacting of some cables which come from a pylon or from a mast. So actually the thing is now how to make a bridge of 70 or 66 meters without having a cable structure. Yeah? And actually there are two possibilities. One possibility is you can make a cross-section which works in bending, which has a compression cord here somehow and a tension cord here. And you can think about of how to integrate the spiral into a cross-section. Yeah? That would be a bending concept. But if you make a pre-calculation, then you will find out that the cross-section here at the top will be of about 1.50 meter diameter, and this will not work. And the simplest concept is you go for a stress ribbon bridge. When you have here a tension element which has to be anchored somehow and this is only like a cable under tension, and that's the basic idea here. But these structures are very lively, and we did a lot of calculations to convince the checking engineer that there will be no fatigue and no ultimate limit state problem with all the vibration stuff.
Or did you make some research? Sorry. Did you make some research on the material to change the resonance or the frequency where this movement start to enter in resonance? Did you change this with the material?
So actually, your question is a good idea. So if you are talking about pedestrian bridges, if you're talking about beam structures, then it's a nice idea to change the natural frequency by adding stiffness or reducing mass or something like that. But if you are talking about this bridge, or where I have shown this example, let's see, where is it? Sorry, this one here. This has natural frequencies in a critical range of about, let's say, 15. There are 15 different modes which are all prone to pedestrian-induced vibrations. So actually, this is not the right way to solve the problem, because you cannot shift all the natural frequencies out of the critical range. And the critical range for these pedestrian bridges is about from 1.8 to 2.5 hertz. And for this bridge, we had about 15 of those critical frequencies in there. So we thought about different ways to solve the problem, and one of these problems, or one of the solutions for this problem, is to increase damping, just to reduce the accelerations.
My question is regarding the your methodology for calculations in irregular geometries. How do you go by applying or developing all these calculations? For instance, in this helicoidal bridge, or when you have conditions that are constantly changing, how do you develop your calculations? Both dynamic, I mean more dynamic than static.
Yeah. So actually changing boundary conditions means that there's a process between architect and engineer in the planning process. So actually we have a basic tool, this finite element program. You see some pictures here. This is something the students learn and we use all the time in our offices. And we have at the end of the day, we have, let's say, 10 or 20 models where we change the boundary conditions in the model and make some optimization, try to figure out which design is better than the other one, where can we save material, where don't we have these dynamic problems. And so actually this is also in an engineering office, this is a kind of process where we have to develop the ideas, because in this case, we studied, for instance, several mast positions, the height of the mast, and also the number of hangers here. We have several models to test it, and the keyword is all finite element programs to make calculations and to see how the structure will react. The problem is in the design, or not the problem, but the challenge is that you have a whole bunch of parameters. You have on the one hand the material, the cost, you have cross sections, dimensioning of this, all the parts of the bridge like the cables and the masts, so you have to care about the static ultimate limit state, and at the end of the day also of the dynamics. So it's always a kind of compromise. But from my experience in the design office, it's not a clear, straightforward. It's always like looking for better solutions and trying several options. Pardon?
And then the jumping guys.
And the jumping guys at the end, yeah, to evaluate your calculations, very important.
Do you get the same type of problems with cable net structures or suspend net structures in general for towers?
For towers, cable net structure. So, actually, these cable net structures, they have a lot of tension, and actually they help us to increase the natural frequencies. You know it from a guitar. If you put tension on the string, the tune will go up, and also the natural frequency. So these structures are a little bit better. They have higher natural frequencies, and actually for cable net structures, roof structures, it's not that big issue, because the wind excitation is not that big, and actually even if you have a very lightweight structures and no mass acting against an acceleration, it helps because the natural frequencies are very high. So we had, Schlaich bergermann had never some problems with these cable net structures up to now, or with these membrane roofs.
How do they compare to compression structures?
Much better, because they cannot buckle. That's a big issue. But to be honest with you, we have also in these structures, we have, let's see, on this structure here, we have a tension element here, but we have also a big compression ring here. You cannot avoid compression, but reduce the elements with compression. That's the basic idea, because you know, buckling is some of the problems we have to face if you have compression in a member.
I would like to ask, because I found very interesting the part of the, first of all, in your conclusion as well, you are tackling the issue of materials as a solution to the different problematics of the lightweight structure, but as well, you have shown this example of the very thin ribbon of carbon fiber. And I guess, especially in research, but as well in the practice of Schlaich and partners, you are collaborating with material engineers as well, or you're trying in a way do you work with new composite materials, trying to figure out new materials that could solve these problems in the lightweight structures? And if yes, I would like to ask, which are the newest materials that you have come up with in order to work on those structures, in terms especially of composite materials, which I guess that's the tendency now in order to solve this problematic.
So actually, we are not working with chemistries or material engineers together. We have a cooperation with SGL Group. I don't know if you know them. They produce carbon fibers, and they are interested to introduce carbon fibers into the construction market. They have a lot of carbon fibers for BMW and for Mercedes for cars, and that's a typical application for these carbon fibers, high-end products. But they also want to have some tension elements which can be used here. So there's a collaboration, and we try to develop not the material but the structural element of a tension element. Because the problem is, it's not a problem to have cable structures or something like just a stress ribbon. The problem is the anchorage of this, or how do you get the forces from the stress ribbon, which is made from carbon fibers, to the other parts of your construction. And I want just to show you the problem here in this picture of the stress ribbon bridge, but it's a little bit too slow here. Let's see. This picture. So the problem you can see here is not this kind of lamella. This is something you can use and you can buy. The problem is how to anchor this lamella and how to make the anchorage of this, because in this anchorage you can lose a lot of bearing capacity. So if you, for instance, take this lamella and glue it, you have only 10% of the strength from the original. So actually this is a very important part, and this carbon fiber company is interested in how to solve this problem here. But they have a material lab, and when we go for a meeting and ask for a special structure or special material, they ask their material engineers. But you see, from Technical University Berlin, it's a little bit complicated because not all of the institutes or chairs are working on this stuff, so we are looking for cooperation. But in this case, we have more or less a development which is closed into a company.
I'm wondering, when you talk about material economy and achieving lightweight structure and the different loads you have to resist, like when you talked about buckling and all that, a lot of, apart from your detailed design, a lot of the possibilities are already set by the forms that the architects choose to some extent, because some shapes and forms will make a very big influence on. So I'm wondering how much of an influence in all your works, when you've worked with architects, how is the back and forth that goes on between yourself and them in the conceptual stages, you know, or do you have to face the forms that they already decide and limit you already in the beginning?
Actually, you see two extreme points. One is the pedestrian bridge with an artist who said he wanted to have a great picture. And he knows that it's not easy to go over 66 meters or 100 meters. So actually he just, in this case, we have done several designs and discussed with him. But he has not a concrete vision of a form. You see, he wanted to have the idea of the spirals. And we can discuss how we can realize this more or less. So this is one extreme. Then we have these footbridges where no architect is involved. There we do the design for ourselves. And then we have the stadia roofs. For instance, like this Warsaw Stadia, which was done with Gerkan, Mark and Partner. And actually, I know the design process there because I was involved in the competition here for Barca Campo Nou, where GMP has not won. But actually this was a nice experience because they give us a very good idea or impression what they really want to have at the end. And actually we are trying to make a roof structure which comes to this idea at very close. But they don't give us a form. And we developed 6 or 7, something like that, different options for stadia roofs. And this is always a kind of process, because then actually they play around with these different roof structures and see, okay, this is something we want, or no, we don't want, we want to have a shape like this. For instance, the Kapstadt Stadium is a very good example, because you know it has a very smooth form, and actually this is a kind of process where we always we're asked to go for the limits of the structural engineers, but actually we have to study and to see if it's possible to realize what they want to have. And this is a very interesting but also a very hard process, because sometimes you go to the office of Gerkan, Mark and Partner, you have 8 proposals or 6 proposals, and they look, no, and you have to go and do your homework again. So it's. But at the end of the day, you see the One interesting point is that this is a team which works for several structures together, which had already worked on several structures and are also working in competitions together. So you know each other, you know what is possible, and actually if you are talking about stadio roofs, then there's a large variety of possibilities, and they say we want to go more in this direction or more in that direction. So actually the benefit from a long cooperation is very good in this case if you want to make a competition for this kind of roof structure.
In the damping example that you showed, the expansion contraction element is perpendicular to the resonance and is underneath. And in the muscle example that you showed at the end, the expansion contraction element is parallel to the resonance but is offset from the axis. Yeah. Yes. Is it possible to move the expansion contraction element so that it is on axis with the resonance, or to have one that is perpendicular but is above rather than below?
The problem is so the first concept of the tuned mass damper is just to get a mass vibrating and acting against a dashpot which will dissipate energy. Let's see if I have these damping here. This is a typical damper for this one here, for vertical vibration. You put this on a deck and this mass will start to vibrate in this direction and act on this dashpot here. And actually, if you are talking now about this active vibration control, we are introducing here forces. And the problem here in this case is, or I will show you the video again, this one here. Now, think about different mode shapes which are possible for these structures. So the first one will be a bending mode which has a mode shape like this and vibrates up and down. So upper position, lower position, goes up and down. And in case of the tuned mass damper, I would put the tuned mass damper here in the middle where I have the maximum acceleration, and the mass damper will be excited in this direction and working in this direction. But now the problem is, if you want to have another concept where you introduce active forces by this muscle, you have to think about how to introduce these forces, for instance, also for several mode shapes. You have the first mode shape is this, with one belly, and the second mode shape looks like this. Two signs here, one up and down, with two bellies. And in this case, you always want to use the same muscles. So you are not sure that for this pedestrian bridge, the first natural frequency is excited, or the second, or the third. So actually, we take a lot of more tuned mass dampers, and the basic idea is, if you, for instance, walk across this bridge and the bridge starts to vibrate in the first natural frequency, then actually you have something which is comparable to something which is bending. You will have here compression and here tension. So if it gets down, and if it goes up the other way around. And the idea is now to introduce forces acting against the vibration of the pedestrian. And this is the video where here's nobody on the bridge, and you see the muscles introduce the forces, and you get a vibration like this. And if you get now a right time lag between the vibration of the pedestrian and this one, then actually if you add now this vibration to the vibration of the pedestrian, you will have deflection zero. That's the basic idea behind that.
So what happens if you move the muscle in the axis of the bridges?
Here, you don't have a lever arm anymore. The problem is now you have a lever arm, this one here, and you have a... if you put it here, it goes down to zero, the efficiency. So actually the problem is that you want to have something like bending. And to have this, you introduce here forces, and so these forces produce a bending moment to this structure here. And if you go down with this muscle down here, it has no efficiency.
The bending element is on the bottom, yes. So if you had muscles in between the concrete pieces at the top of the concrete pieces, you still have an opposite.
So if you put it here on,
you have just one layer of material that is not that thick that could expand and contract in the way that the muscles are.
So if you want to have a very thin concrete plate, you have to introduce somehow a bending into the whole structure here. The problem is, if you put, for instance, here at the upper edge of this concrete, this muscle, the system line is somehow here in the middle of the concrete plate. You have a lever arm of 5 or 6 centimeters. And in this case, we have the height of the post. This is about 1 meter and 20. So actually, you can have here the same moment with a very small force, because the lever arm is longer. And that's the trick here. Actually, if you wanted to have no posts here and no of the muscles over here and your very thin plate here, it's not possible to introduce the bending into this bridge anymore.
In which direction do you think lightweight structures are going in the future, in terms of the types of structure we'll be able to make, as well as materials and other innovations we might see? Will they become mainstream in the future, or will they keep on bridges and like other structures rather than buildings?
I think that membranes or these cable net structures and all these lightweight structures have a certain market. For instance, for long and wide span, and let's say also for the kind of towers. But it's not the main issue of construction industries. So if you look at the amount of concrete used every year compared to the amount of membrane which is used every year, it's a huge difference, you see, because housing and everything is a kind of, or for instance, buildings for offices, or this is all done with steel or concrete. And you need special applications like long span bridges or very big roof structures to have a market for these membrane structures. Actually, you see, this vibration problem comes also up in office buildings, because they try to make it more lightweight. It's a different story, because then you are talking about these slim floors and everything. So they try to reduce the thickness of the concrete and reduce the number of girders in this slab system. But they will also end up with vibration problems, and this is something which is also a trend in the, let's say, normal construction industry to save material. But I don't think that cable net structures will expand dramatically in the near future. There will be a market. And let's see what is after the Brazilian World Championships. How many stadiums do you need in the future? So this is a classical application. And if you decide now to make a roof structure for horse race or camel race, that's a new market. But actually you need somebody who is interested to do for this. I think for bridge design, there is the tendency to make the structures more efficient, more long span, and then you have to think about new materials like carbon fibers or something like that, because steel has reached now some limits. I think in bridge design the new materials have more impact in the near future.
I don't know if it's a full question, but as well as we are talking about lightweight with light bridge, but then they have such a big pillars, such a huge structure, which in some way are not so light. And I mean, is possible, or are there cases where you can kind of hide this and according with the surrounding make I don't know, hide, if you build a bridge in the mountain, use the rocks as the structure, or a building close to it, just because actually it seems like a fake flight. It's like parents keeping a child. So that's it.
Good point. So actually, if you look at this bridge, it looks very lightweight from here to here, but you have these large abutments. So actually, you need a lot of mass or a lot of effort to put or to anchor these tension forces in the ground. And this is one disadvantage of lightweight structures, because you try to stabilize everything with tension forces, and at the end of the day you have to anchor them somewhere, somehow. And there are several examples. For instance, there's a famous Swiss engineer, how is it called? Jörg in Switzerland. He builds also stress-ribbon bridge, but he anchors this in the rock. Very efficient, very nice bridges, but in this case you don't have this rock. You have to have some bore piles and everything and anchorages to anchor these forces. That's right. But in case of these stadia roofs, there is, to my mind, no alternative to make it lightweight, because if you deal with these structures as a compression and tension system like we have here in these stadia roofs with this membrane structure, is much more efficient than compared to a structure where you have poor bending. So if you try to make these stadia roofs with cantilevering systems just with poor bending, you will get double or 3 times more mass. So actually in this case it makes sense. And you don't have to have these big foundations for the stadias. So in this case it's real lightweight structures. But if we are talking about stress-ribbon bridges, then you have the problem that you need big abutments. The story is completely different also if you take suspension bridges, because you can self-anchor them. So you have here you have a system where you have, let's see where it is. This one here. So this is not fully anchored, because actually you see the cables here collect the loads here by these hangers, and you have these backstay cables which have to be anchored. But if you have a straight girder, you can also introduce these forces again into the deck, and then it's a very easy construction, because the concrete is happy. You give him compression in this deck, and actually you don't need these big abutments. So this is a kind to make these structures more efficient in terms of foundation.
No, and thank you very much. We have some time to discuss more informally Has been great to have you here. Thank you very much.